All right, so today we're going to finish our review of midterm material. And our list of things, let's see, I'll put up a Word document so I'm not projecting nonsense on the screen. Okay. So the list of things that we need to go over and finish for today: intermolecular forces, non-ionic equations, empirical formulas, predicting products of reaction, stoichiometry, and solution stoichiometry. This was the stuff that you guys listed off on Wednesday that we just didn't get to. Is there anything that we need to add to this? It's already kind of long list, but we can be speedy if you want to add anything else to it. We good? All right, let's do empirical formulas first, because I have a when I make up empirical formula problems, they come out to be nonsense, and then you're like looking at me going, well, that molecule doesn't exist, Dr. Bruck. And I go, yeah, I know, I just made it up. So I'm going to use some real data. So you have to be given data to do an empirical formula and then convert it into a molecular formula. So here's some real data. A compound with a molar mass of approximately 142 grams per mole is 50.7% carbon, 9.9% hydrogen, and 39.4% nitrogen. What is its molecular formula? So, do you remember the difference between an empirical formula and a molecular formula? Does anyone remember? Empirical versus molecular. Right, this is the lowest ratio. It cannot be reduced, right? So an example of that would be CH, right? The ratio 1:1 can't be reduced any further. Versus a molecular formula is reducible. So for example, C6H6. There's no such molecule as CH. That doesn't exist. There is C6H6. That's benzene, right? That's a ring that looks like this. Every other one is a double bond. All right, so an empirical formula cannot be reduced any further. A molecular formula can be reduced. You can calculate your empirical formula and then turn it into a molecular formula. So anytime you see percentages like this, you need to think to yourself, okay, I've got to calculate an empirical formula. And then if the problem asks for a molecular formula, then you would just take it a step further. So I'm going to take this information down so that I can write on the screen without the words. 50.7% carbon, 9.9% hydrogen, 39.4 nitrogen, and its molar mass is 142. Okay. So let's go back to here. Okay, so step 1, we're going to calculate the empirical formula. Step 1, we're going to convert grams to moles. So we are going to pretend that we've got a 100-gram sample. Okay, we're just going to pretend for the sake of argument that this is a 100-gram sample. If it's a 100-gram sample and it's 50.7% carbon, how many grams of carbon will we have? 50.7, right. So we're just going to take all those percentages and drop the percent sign and replace it with a G. So 50.7 grams carbon, 9.9 grams hydrogen, 39.4 grams nitrogen. We're going to convert all those to moles. So we need our calculator. Molar mass of carbon is 12.011. Molar mass of hydrogen is 1.008. And molar mass of nitrogen is 14. We're going to carry out lots of extra decimal places because we'll need to worry about, we don't need to worry about sig figs at this point. 12.011. So I get 4.2211. 9.9 divided by 1.008 gives me 9.8214. And 39.4 divided by 14 gives me 2.8149. So that's step one. Step two, we're going to divide through by the smallest number moles. All right, so I look at my three numbers here. 2.8149 is my smallest, so I'm going to divide everybody by that number. And that will give me my mole ratios, which are my empirical formula. So 4.221 divided by 2.8149 gives me 1.4995, which we're going to round to 1.5. We'll deal with this in just a minute. 9.8214 divided by 2.8149. That also gives me a 0.5 ending, and then this was 1. So anytime when you divide through, if you get a number that ends in 0.5, do you just round it up? No. The answer is no, you don't. What do you do if when you divide through by the smallest, you get a number that ends in 0.5? You double not only it, but all of them, right? So we're going to double all of them. Okay, my molar mass is in the way. 142. Okay, so that becomes 3. That becomes 7. That becomes 2. So my empirical formula is C3H7N2. What if at this step we got an answer that ended in 0.3? That's like a third. What would we get? What would we do there? We triple everything. And now, otherwise, you just round up or round down. Okay, so if you got an answer that ends in 0.2, you got an answer that ends in 0.8, right? You just round up or round down. 0.5, you double everybody. 0.3, you triple everybody. So this is my empirical formula. And you can always check your work by asking yourself, does the ratio 3 to 7 to 2 reduce? No, it doesn't. So I know that it's an empirical formula. But the problem didn't ask for the empirical formula, the problem asked for the molecular formula. So to calculate the molecular formula is really easy. If you made it through this, calculating molecular formula is really easy. You take the molar mass of the molecular, which is given, and you divide it by the molar mass of the empirical, which you calculate. And whatever that number comes out to be, multiply all these numbers by that number. So the problem told me that the molar mass was 142. 142. And then I've got to calculate the molar mass of what I just came up with. So 3 times 12.011 plus 7 times 1.008 plus 28 gives me 71.089. So 142 divided by 71.089 gives me 1.997, which we're going to round to 2. So therefore, the molecular formula is just 2 times this. So it would be C6H14N4. Does everyone see how we calculated the molecular formula? How we got the empirical formula? I would have to give you that molar mass. You couldn't do this without me giving you the molar mass. You have to have that information. Does everyone see how we did this problem? Does that answer the question of whoever it was that threw out your formulas? Does that answer your question thoroughly enough? Okay. All right, so the next thing we're going to do, projector on anymore. Save the bulb. Next we're going to do on our list is predicting products of reactions. Was I even in the frame? Oh, good, I was. All right, so we're going to do predicting products of reactions because that kind of leads us into net ionic equations and solution stoichiometry and all that good stuff.
The fun stuff.
That is fun stuff. All right. So predicting products. Not to put you on the spot, but is there any particular kind of reaction we want to predict products of? Whoever it was that threw that out. Do you have any particular kind of problem, reaction we're working on? I don't remember who. Nothing specifically? Okay. So let's just make up some, let's do some double displacements because that's probably the biggest place where we ran into error. Let's do magnesium dichromate is formed from reaction between ammonium dichromate and magnesium nitrate. What is the reaction? Write a balanced equation for this. Dichromate is a polyatomic ion that students mess up a lot. So we can roll a lot of things into this one. We can review our polyatomic ions. We can review formula writing. We can review balancing equations. We can roll a whole lot of skills into this one problem. So it says is formed. So does that mean it's a reactant or a product? It's a product. So let's not worry about it first. Let's worry about what our reactants are. Our reactants are ammonium dichromate and magnesium nitrate. So what is the formula for ammonium? Who knows? What is it?
NH sub 4.
NH4 with what charge?
It's a negative one.
Positive one. Right.
Awesome.
Ammonium is NH4 plus, and what's dichromate? Cr2O7, right? What charge? 2 minus. Good. So when we write this formula, when we crisscross, right? 1, 2, that gives me the formula NH4 2 Cr2O7. Right, so there's our reactant. And then what's magnesium when it's an ion? What's its charge? Magnesium's in group 2, so what's its charge? +2. And nitrate is, and what's the formula though? NO3 minus, right? So the formula here, when we crisscross, MgNO3 2. So even if we didn't know what the product was, even if I didn't tell you this top part, what if I just said, write a reaction between ammonium dichromate and magnesium nitrate? Like I could even just do this part right here. Even if I didn't tell you what the product was. If I just said, write this reaction, you could do this, right? Because this is a single and this is a double displacement reaction, right? The cation of the first compound gets together with the anion of the second, right? And the cation of the second gets together with the anion of the first, right? So like two couples break up and start dating each other. That's what you can think of, right? So that means that my products are going to be ammonium nitrate. So let's rewrite that formula. Ammonium is going to be NH4 plus. Nitrate is NO3 minus. So when I crisscross those, do I have any subscripts? That's a 1-to-1 ratio, right? So that's NH4, NO3. Am I still in the frame? Yes. And then we already know our other product because I told it to you in the problem, but let's prove it to ourselves. Right? Magnesium and dichromate. Oops, 2 minus. 2 plus and 2 minus. Right? So, magnesium plus 2, dichromate minus 2. So this is a 2 and 2. So does that need any subscripts as well? No, no subscripts needed, right? Because that's a 1-to-1 ratio as well. So that would be MgCr2O7. All right. Now all we need to do is balance this. Is this a balanced equation? What do we need to do to balance it? A 2 where? That's right. And is there anything else we need to do to balance this? Now, if this were a solubility problem, if I said, what's the precipitate here, you'd have to break out your solubility rules, which I will give you on a test. Your solubility rules are in your textbook, which there it is. Oh, I had our textbook here. I don't remember what page they're on.
Like 316.
Okay. Word for it. Uh, 316 is in the quantum theory stuff. Let's just look it up. Solubility rules. 161, it sounds like. Slightly off. But there are like 1,000 pages in this book, so. There we are, yes. All right, so if this were a solubility problem, I'd give you the solubility rules for you to pick out what the product is. Now, actually, the solubility rules I'm going to give you look slightly different from this one because I remember looking at this one and thinking it's kind of anemic. The one that I give you is a more comprehensive solubility chart. And if you've been on the course webpage, you've seen it. That's the solubility chart I'll give you on an exam. But if I said, okay, what's the precipitate here? If these were 2 aqueous solutions being combined, this is soluble because all salts containing ammonium are soluble. So you don't even need to look that up. This one's soluble because all salts containing nitrate are soluble, so you don't need to look that one up. Now, here, ammonium nitrate, all soluble, therefore that one's soluble. But dichromate's soluble with very little. It's soluble with ammonium. It's soluble with group 1, but this is not group 1. This would be your precipitate. If I asked you what was the precipitate, that's what that would be. Okay. Let's do one more predicting products type problem just for fun. Just to make sure that we've got a good grasp on it. Let's do solutions of sodium sulfide and lithium actually, let's not do lithium because I don't want it to be no apparent reaction. Let's do copper 2. Is copper 2 soluble as sulfide? I can't remember. It might be. Let's think of one more. I'm trying to think of something that will precipitate out sulfide. I think copper 2 would be soluble. Let's do chromium. Chromium 3 chloride. I've already revealed that sulfide is going to be precipitated out, but let's confirm that. All right, so sodium has what charge as an ion? Plus. And sulfide is what? What's the formula and what's the charge?
Just S.
It's just S, right? And what's the charge?
-2.
-2, right? Don't confuse sulfide and sulfite, right? Because those two sound very, very similar. Sulfide versus sulfite, right? Very, very, very similar sounding. IDE suffix means it's from the periodic table. It's a monatomic ion. And chromium 3, that 3 tells me that it's Cr3 plus, and chloride is what? It's just Cl minus, right? So this would be Na2S. This would be CrCl3. This is also double displacement. So sodium is going to now be with chloride. So Na plus Cl minus. And our other product is chromium 3 and sulfide. So this will be Cr2S3. Is this balanced? Let's clean up our work here. Is this balanced? No, it's not. Now you can make a reactant and product table if you need to, or you can just do it in your head. What do we need to do to balance this? Or do you want to make a reactant product table? Does anyone need to see how that looks? You want to see a reactant? You want to do it? Okay. So if you can't do it in your head, that's fine. Make yourself a reactant product table. You just list all your reactants and your products. Na, write them in the same order. Na, we've got 2 and 1. Sulfur, we've got 1 and 3. Chromium, we've got 1 and 2. And chlorine, you've got 3 and 1. So you really just pick something and start playing around with it, right? Where do you want to start? You're going to end up going back and changing these, so it really doesn't matter. Where do you want to start?
Sodium.
Okay, how do you want to balance sodium?
You would put 2 in front.
To start out, let's start with putting a 2, yeah. So we put a 2 here, distribute it. We're already going to see where this is going, though. That 2 is going to end up becoming a 6, right? But let's demonstrate why. Okay, let's fix the chlorine. The sulfur next in line. If we put where's the sulfur over here? We put a 2 here, we would make that a 2. Oh, I put a 3 here, that make that a 3. And then we start getting into problems of least common multiple, right? Because 3 times 2 is 6, 3 times 1 is 3, right? Now we're going, well, now what? I messed up my sodium. I can go back and change that to a 6. This is also going to get wonky here, because does a 3 turn into a 2, or does a 2 turn into a 3? No. The least common multiple of those two would be 6. Right? So if I go back and change this here to 6, 6 times 1 gives me 6. And now this is easily fixable, because if I put what right here, does the rest get balanced? 2. So sometimes you have to go back and change, but a reactant product table helps you keep it visual, right? If you're a visual person and you like seeing things visually organized, visual as organization works all the reactant product table. If I said, what's the precipitate here? Chromium compounds are very rarely soluble unless they're with like acetate, right, or nitrate. And sulfides are pretty insoluble too. There are a lot of more exceptions with sulfide than there are with like dichromate, but this would be our precipitate. Questions on how we wrote and balanced this equation? All right, we're gonna get through the rest of this. We gotta move. We gotta really hustle. So let's go down the list and do net ionic equations. I shouldn't have erased that actually, because that would have been a good one to turn into a net ionic equation. So I'll just rewrite it up here at the top. Let's see. Read back to me my equation. It was 3 Na2S 2Cr Cl3 6 NaCl Cr2 S3. Okay, thank you. All right, so for writing net ionic equations, if we were doing a solubility type problem and we identified this as the precipitate, we want to write the net ionic equation. So the first thing we need to write is the molecular. That's what this is. That's just a regular old balanced equation. Nothing special about that. What we're going to do next is we're going to turn that into a complete ionic equation, or some textbooks call it a total ionic equation. And what you do here is you're going to dissociate everything but liquid, gas, and solid. So in other words, anything with an AQ next to it, you need to dissociate back into its ions. And you would need to distribute any coefficients. So students really have a lot of opportunity to mess up here because you've got to uncrisscross what you just did here, and you've got to distribute any coefficients. So when Na2S dissociates, breaks apart into its ions, right? How many sodiums are you going to get? 6, right? Because there are 2 in the formula, but there's a coefficient of 3. Good. So this would be, I'm going to need lots of space. Am I in the frame at all? Yes. 6 Na plus how many sulfides? 3. 3 S2 minus plus how many chromiums? 2. Right, 2 Cr, 3 plus. Is it okay if you leave the charges off? You just want, like, I don't want to write them. Is that okay? No, because is chromium the metal the same thing as chromium 3, the ion? No. And then how many chlorides do we get? 6. Produces, now we're just going to carry this one through. 6 Na plus 6 Cl minus, and then we're going to leave the precipitate alone. It's a solid, leave it alone. Cr2S3 solid. So that's the complete ionic equation, or total ionic, depending on which textbook you're looking at. But notice there's a lot of redundancy here, right? Because you see the same thing on the reactant side and on the product side. If it starts out the same and ends up completely unchanged, did it really participate in the reaction? No, it didn't, right? What do we call those? Does anyone remember? Like this 6CO minus, it's not doing anything. It's a spectator ion, right? So what we do now to get the net ionic equation, you remove the spectators. So let's see, we've got Na plus and Na plus, and they should match exactly. They should match exactly. And 6Cl minus, 6Cl minus, and what you're left with is the net ionic equation. Now it doesn't matter which one you write first, okay? When you're writing the formula, the cation needs to go first. But when you're writing the equation, if you wrote the anion first, that wouldn't matter. So 3S2 minus plus 2Cr3 plus produces Cr2S3 solid. And that is the net ionic equation. Do you feel good about net ionic equations? Do we do more net ionic equations, or does that serve as a Okay example. Can we do one more? No? Okay. So, let's see. We have to finish intermolecular forces, and this is kind of a good place to finish it because solutions deal with that. Solute and solvent matching each other and all that good stuff. So the IMFs that we discussed yesterday briefly, so we've got London, we've got dipole, we've got hydrogen bonding, and we've got ion dipole. There are others, but these are the only 4 that you're responsible for as a general Chem 1 student. Ion dipole is the intermolecular force that causes an ion to dissolve in water. So for instance, this is the one we didn't talk about yesterday, but it's a big part of solutions. For example, NaClAq. When you dissolve sodium chloride in water, the reason that this dissolves is because of the ion dipole intermolecular force. So you would have, here's your cation, and here's your anion. Anions are bigger than cations. And here's water. And water surrounds the cation or the anion. It surrounds both. Why am I drawing it this way? I am specifically drawing the oxygen facing in for a specific reason. If this is the Lewis structure for water, where is the partial negative charge on which atom? On the oxygen. Oops, that's an 8. That's the Greek letter delta, lowercase. Right? You've got a large positive here. So why would the negative, large negative here, why would the negative face in? This is positively charged cation. This is the negatively charged dipole, right? So they are attracted to each other. This process is called solvation because water is the solvent. How's the water going to be oriented around the anion? Right, with the hydrogens facing in. So that is what the ion dipole intermolecular force looks like. That's the reason why ionic substances dissolve in water. Why would an ionic substance not dissolve in, say, if you combine in heptane, which has the formula C7H16. Here's its Lewis structure. 1, 2, 3, 4, 5, 6, 7. And then all of these. 1, 2, 3, 4, 5, 6, 7. All of these parts where I got lazy are all hydrogens. Why would NaCl not dissolve in heptane? Nonpolar, right. The intermolecular forces must match. They must be compatible with each other for a dissolving to occur. This is highly, highly, highly polar, right? This is an ionic compound, so it's very, very polar as well. Polar, polar, IMFs match. The ion dipole intermolecular force is what drives this to occur. Solvation occurs because of the ion dipole IMF. No dissolving occurs here because this only has London forces, right? I know I'm way out of the frame. Oh well. Not polar. right? If you're not polar, then you're not going to have something polar dissolve in you. How far out of the frame did I go? Pretty bad. There you go. All right, if something is nonpolar, then obviously a polar solute can't dissolve in it, right? The intermolecular forces don't match. All right, I think that kind of wraps up ion dipole. Do we need to do any more with it? It's really all you need to worry about ion dipole with. Do we need to go back and review any of these other IMFs from yesterday? We went through them a little bit quickly. You want to go back and review any of those? That was really the only one we didn't get to yesterday. Okay. Let's do a regular stoichiometry example, and then we'll do a solution stoichiometry example. Because if you don't understand regular stoichiometry, then it's probably kind of a wasted effort to do solution stoichiometry. So let's just do a good old classic stoichiometry. And there are 3 steps. And this is just your classic traditional stoichiometry. Let's do an easy equation. H2 gas and N2 gas produce NH3. How much product forms from 10 grams H2? So this is regular old stoichiometry. What's the difference between stoichiometry problems and limiting reagent problems? In a limiting reagent problem, you know information about both reactants, right? In a regular old stoichiometry problem, you'd only know information about one. So we'll do this as a stoichiometry problem, and then we'll turn it into a limiting reagent problem in a minute, just for fun. And that's a D, by the way, how much product. Just get lazy. All right, first we have to write a balanced equation. H2, N2, NH3. Is this balanced? No, it's not. What do we need to do?
Put 3 onto the H2, put 2 onto nitrogen, then double the NH3.
Here? Let's see. 3 times 2 is 6. 2 times 3 is 6. 2 times 2 is 4. 2. Do we need this? No. There we go. Okay, now what I do is I write what I know underneath it, and then I put a question mark next to the thing that I'm looking for. All right, so the first thing I want to do, stoichiometry is 3 steps. First step is we're going to convert grams to moles for H2. So 10 grams to 0.016, right? Because each one of them is 1.008 grams per mole. And so we 10 divided by 2.016 gives me 4.960317, blah 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 blah. We have to have 2 sig figs in my final answer, so I'll just carry 1 extra. Second step is we're going to multiply by the mole ratio. Mole ratio comes from the balanced chemical equation. So 4.96. Nope, not grams. 4.96 moles. For every 2 moles of H2 that I use, oh, excuse me, for every 3 moles of H2s that I use, I produce 2 moles of NH3. So take my answer times 2 divided by 3. That gives me 3.307 moles NH3. And now my last step is the problem asks for how much product. I didn't say how much product, let's say in grams. So I convert moles back to grams because the problem dictates what I'm going to do in step 3. The problem asks what is the mass in grams, so I need to convert that to grams. So 3.307 moles NH3, 17 grams per mole. Yes, I know it's not technically 17 point on the nose, but that's okay. Oops. 3.307. .1.
Why isn't the moles on the bottom?
Oh, because I wrote it backwards. Thank you. 17 grams per mole. Thank you. Moles need to cancel. 3.307. Keeping 2 significant figures, that would be 56 grams. Now, if this were a limiting reagent problem, what if I said forms from 10 grams H2 and 12 grams N2? How would we change this problem? We'd have to do the whole thing twice, right? We do all this work again, now from the 12 grams. And then we pick the smaller number. Okay, so anytime you know information about 2 substances, it's a limiting reagent problem. You'd have to do all the work twice and pick the smallest number. Do we feel okay about that? Do you want me to go through it? I will. Do you want me to go through it? Feel okay? I think you'll see limiting reagent problems when we do solution stoichiometry. Because I'm going to do several solution stoichiometry problems right now. So I'll give you a second to jot that down if you're still writing. Well, I enjoy a juice box that I swiped out of my van. I keep these in my car for my kids. And I was really thirsty and I didn't have another drink. So. Thanks, kids. That's right. I paid for it. It's mine. It's not theirs. It's mine. I just share, right? Spoken like a parent. Okay, let's do a solution stoichiometry. Solution stoichiometry is kind of amorphous, right? With regular old stoichiometry, there's always a step. Step 1, you do this. Step 2, you do this. Step 3, you do this. But when you're dealing with solution stoichiometry, this one kind of can bite you in the rear end because it's not always going to be exactly the same every time. Solution stoichiometry, your steps are based on what your problem tells you. Okay? So that's where, you know, you can really get into some hot water if you're not closely watching. So let's do, I'm just going to write the equation, and then you decide if it's balanced. Oops. Let's precipitate out something. Is this balanced?
No.
It's not. What do I need to do to balance it?
For the KOH, you put a 2 on it. It's KCl.
All right. Now balanced. Okay, let's pretend that the problem says you have 500 milliliters of 0.11 molar CaCl2 with 450 milliliters of 0.15 molar KOH. What mass of precipitate forms? I'll give you a second to jot down the problem so you're not trying to write while I'm talking. Now here's what I do, and I would strongly recommend that you do this as well. List your information under the problem, what you know and what you're looking for, so you don't plug in the wrong stuff in the wrong place. Also, go ahead and convert milliliters to liters. Why? Why do you want to do that? We're going to be using the molarity equation. Molarity is equal to what divided by what? Moles divided by liters, right? Not milliliters. So to convert milliliters to liters, what do I do? 3 to the left, right? Divide by 1,000. So we've got 0.500 molar and 0.0500 liters. And it's 0.11 molar. And we've got 0.450 liters, and it's 0.15 molar. And we want to know what mass of the precipitate can we get. Mass is always grams. I mean, you could convert it to kilograms, but it wouldn't be very much. You could convert it to milligrams too if you wanted, but it needs to be a mass in some version of grams. Right? A mass is not measured in pounds or ounces. Okay, so first thing we need to do is look at our problem and say, what kind of problem is this going to be? Regular stoichiometry or limiting reagent? Do I know information about one substance or more than one substance?
More than one.
More than one. So I'm going to have to do my stoichiometry twice, right? Because I know information about two things. So let's do the stoichiometry going from here to here and then here to here. All right. For calcium chloride. Now, the first thing we want to do in any stoichiometric problem, be it regular stoichiometry or solution stoichiometry, in step 1, you need to have moles as your outcome, no matter how you get it. Whatever you have to do to get moles, that's what you got to do. So in our last problem, we just converted grams to moles, easy peasy. Here, if I've got a molarity and a volume, how can I get number of moles? We're just going to use the molarity equation, right? Am I in the frame? If molarity is equal to moles over liters, then moles is equal to what?
Molarity times liters.
Molarity times liters, right? I always underline M to show that it's molarity so that it doesn't be confused with little m, which is molality. And we'll talk about that on Monday. That was part of this week's stuff. Little m is molality. And it was actually one of the ones you learned already as well. But we haven't talked too much about molality yet. So step 1, let's get moles. Moles is equal to molarity times liters. So 0.11 moles per liter times 0.500 liters, right? Liters cancels. Now, if you want to go ahead and set up the next part of the problem, you could do that. You could do this as a 2-step problem and do it all at once if you wanted to. I really wouldn't recommend doing that, though, until you're good at each step of stoichiometry and you can kind of think 3 steps ahead. So let's just do it 1 step at a time. But in the next problem, I'll show you how to do it as kind of one big long. And then that way you can decide if you want to do it that way or not. 0.11 times 0.5 is 0.055. And that's moles of CaCl2. Now, step 2 is always still the mole ratio. Step 2 doesn't change. Whether it's regular stoichiometry or solution stoichiometry, that part doesn't change. So I take my answer and rewrite it, 0.055 moles CaCl2. For every 1 mole of calcium chloride that I use, I produce 1 mole of my precipitate. So my number doesn't change, but my units do. And yes, I do still want to see this step in your work when you're showing your work, because I want to know that you know how to convert from this unit to the other unit. So 0.055 moles CaOH2. And now the problem asks, what's the mass of the calcium hydroxide in grams? So that when I put it on my balance, I know what its mass is. So now we're just rewriting this. 0.05, that's a decimal. Now we got to calculate its molar mass. So 2.018 plus 1632 plus, what's calcium? It's in the 20s. No, excuse me, it's in the 40s, 40.08. 74.098. All right, so times 0.055 gives me 4.075, which I then round to, how many sig figs do I keep? This one's got 3, this one's got 2, so my final answer needs 2. So that would be 4.1 grams. So make myself a note. From the CaCl2, I got 4.1 grams. Because I'm not done yet, am I? I've got to do all this again because I know information about both reactants. Anytime you know information about both reactants, you got to do the calculations twice. So, can I erase the board? Is anyone still jotting this down? The video will be posted this afternoon, so if you want to go back and look at it, you can go back and get it if I'm going too fast. Because I do want to get through another kind of solution stoichiometry problem before we run out of time. Now we've got to do that again for this one. But I'm going to do it as one big long problem this time just so you can see what that looks like. Because if you're getting good at this kind of stuff and you don't want to write it all out a whole bunch of times, you can do it as one big long problem. So let's look at what that would look like. So we've got 0.450 liters KOH times, what's the molarity? 0.15 moles KOH per liter. So liters cancel. Now I'm in moles. So there's my step 1. Now I'm going to multiply by the mole ratio. 2 moles KOH for every 1 mole CaOH2. So there's step 2. And now I'm going to convert that to grams. 74.098 grams CaOH2 per mole. Does everyone see there's step 3? How we set that one up? Now again, don't do it like this until you're good at doing it as 3 individual steps, because if setting it up as 3 individual steps gives you the willies, then this is definitely not for you yet. Right? You need to be good at doing step 1 and and then taking that answer and then doing step 2, and then taking that answer and then doing step 3. But if you're at that point where you're like, man, I'm tired of writing all this stuff out, you're just giving me hand cramps here, like, can we do something else? This is a lot less writing, right? And you're doing the exact same work. Now you just multiply all the way across and divide up. So 0.45 times 0.15 times 1 times 74.098 divided by 2. You're going to save yourself some writing, but again, don't do it this way until you're good at doing it as 3 individual steps. So 0.45 times 0.15 times 74.098 divided by 2 gives us 2.5. Round that to 2 sig figs. So now we pick the smaller number. The smaller number is, calcium chloride gave us 4.1. This gives us 2.5, so our answer is this. This is the theoretical yield. If I asked, what is the limiting reagent? You would say KOH. And if I asked, what's the excess reagent? You would say calcium chloride. And the excess reagent is the reagent that you had extra of. How do we feel about this problem? Good. All right, I want to do another kind of solution stoichiometry problem because we've still got time to make it through one more so that you can see a different kind. I won't make this one limiting reagent because if you understand how to do one limiting reagent problem, I think you could understand how to do 10 of them. Let's see. Polarity problem. What's the precipitate we haven't dealt with yet? Actually, let's just use that same reaction so that you don't have to write it over on your paper again. We were doing CaCl2 plus KOH CaOH2 plus here's the second kind of problem. You determine you have, let's not do that big, 1.83 grams precipitate. If you mixed 100 milliliters of CaCl2 with excess KOH, what was the molarity of CaCl2 solution? You determine you have 1.83 grams of precipitate. If you mixed 100 milliliters of the calcium chloride solution with excess KOH, that means you've got extra of it, right? What was the molarity of the calcium chloride? Because who's the limiting reagent and who's the excess reagent, that varies from problem to problem to problem, right? It's based on your original proportions. So let's pretend you've made a scenario now where KOH is in excess, and you had excess amounts of it, and you only used 100 milliliters of the calcium chloride solution. You forgot to write down its molarity though. Whoops. You can go back and figure out that molarity using the mass of the precipitate. So we've got 1.83 grams here, And we know that the volume here is 0.100 liters, and we want to know what's the molarity. So what information do we need to get in order to calculate that molarity?
CaCl2.
Right, moles of this CaCl2, and then, do I have everything I need to do molarity? Yeah, I do. So this is using stoichiometry in a different kind of way, but it'll still be a stoichiometry problem. Step one is still going to be get moles. No matter how you do it, you got to get moles somehow in step one. Right? So step one is going to be 1.83 grams CaOH to 74.098. Is that it? Molar mass? We used that in the previous problem. Was that the molar mass of calcium? Yeah. All right, so grams to moles. So 1.83 divided by 74.098. We're going to eventually be needing 3 sig figs, so let's carry out at least one extra. 0.024697. I carried out 2 extra moles. Okay, what's the step 2 of all stoichiometry problems? Any stoichiometry problem you do, step 2 is always going to be what? The mole ratio, right? So 1 to 1, the number isn't going to change, but my units are. So 0.024697 moles CaOH. Oops. CaCl2. I'm writing my conversion factor all wrong. I'm thinking about my lunch. There we go. Number doesn't change, just units. And now, how do I get molarity?
Divide moles by liters.
Right, molarity is equal to moles per liters. So 0.024697 moles divided by 0.100 liters. So we just take our answer divided by 0.1, or just move the decimal, right? 0.24697, which I then round to 3 sig figs. So what is my final answer when I round it?
247.
247. And my units are capital M, or you could have written out moles over liters, either one. How do you feel about that kind of solution, stoichiometry problem? Yes. What if I had given you the molarity and volume of this? Would this be a stoichiometry that's a limiting reagent problem? Yeah, because then I'd have to give you molarity and volume here. You'd have to figure out number of moles and then figure out the smaller one and then plug that in right here. So if I was really feeling mean, that's what I could do, right? It would make you do this twice.
That'd be fun.
It'd be good practice. Look at everything as an opportunity to practice.
Absolutely.
Any other kinds of problems you want to go over? We're pretty much out of time.
Yeah.
Okay, well, have a great weekend, and I will see you on Monday.